Okay, so now I'm going to just introduce how we would build, but in a digital domain, a simple low-pass filter, and also how you would build a simple high-pass filter in the digital domain. So now I'm asking you to imagine that we've taken these signals, like the step function, or maybe like sinusoidal functions, or some other complicated functions of voltage versus time, and we're going to try and filter it. We're going to try and low-pass RC circuit filter it, or high-pass RC circuit filter it, and see if we can accomplish that in digital domain. I think what we're discovering is actually quite simple to build these circuits in digital domain, and then we'll start to realize that there's this whole world of digital circuits that you can construct that can have very sophisticated properties. And that was really the basis for the filters that were built for isolating, detecting gravitational waves, to build very sophisticated digital signal filtering processing that could pick out gravitational waves from the noise, from the background. Okay, so I'm just going to, on the left-hand side, I've sort of showed you that sort of classical analog theory of the low-pass RC filter. So I'll just spend a few minutes walking through these equations. So they describe the analog world of the low-pass RC filter. And over here on the right-hand side, this is the equivalent in the digital domain, digital world, for the low-pass RC filter. So this is how we describe or formulate a low-pass RC filter in the digital world. And we're just going to walk through the familiar and then take this step into the new over here. So if we wanted to analyze that low-pass RC circuit, we might use Kirchhoff's rules, and understanding that that circuit is just a capacitor and resistor in series, and we apply the input across the series circuit of the capacitor and resistor, and then we see the output for the low-pass filter by looking across just the capacitor, or if we wanted a high-pass filter, we just look across the resistor. So to understand the performance of the circuit, we could write down Kirchhoff's rules for this little circuit here. And if we think about this loop here and apply the voltage rule, right? We've got a input voltage, we've got a resistor and a capacitor. And so in this first equation here, I just wrote down Kirchhoff's rules in terms of this loop here, where between these two terminals over here is the input. Between these two terminals of the capacitor is the output. And then the third element in the circuit here is the resistor. So the input voltage is equal to the sum of the voltage across the resistor in terms of the current through it, and the voltage across the capacitor. So that's Kirchhoff's rules. And then I'm just going to fill in my understanding of, like the resistor and the capacitor. And that's just going to allow me to write the this current, which defined the voltage on the resistor, the changing voltage on the resistor, in terms of the rate of change of the voltage on the capacitor. So the current is simply the rate of flow of charge onto the plates of the capacitor. And the charge on the capacitor is simply the capacitance of the capacitor times the voltage across the plates of the capacitor. So understanding resistance and charge, resistors and capacitors, I can replace this current in Kirchhoff's rules in terms of the rate at which the voltage on the capacitor is changing. And so if I do that, I've built this little differential equation. So this ordinary differential equation that relates the input voltage, the output voltage, and the circuit elements, the resistor and the capacitor. So it's this equation that I'm going to use to build the that equation for writing in the digital domain this low pass RC filter. So this equation in the digital domain, I would write like this. There's just the mapping from the analog domain and this equation to the digital domain, and exactly the same equation. But let me just explain that mapping. The input, the voltage input, we were calling that X subscript I. Those are the input samples. The voltage output, we were calling that Y with a label I for the output samples. So here's YI, for example. The rate of change of the output, what would that be? So that's the dV dt for the output. That's the difference between consecutive samples divided by the time interval between consecutive samples. So that would be a corresponding difference equation for that differential. So that's going to be yi minus the prior sample, yi minus 1, divided by the time interval between samples. And so that's this piece here. So this is the rate of change of the output as a function of time. And then here's just the RC that multiplies this differential. And so this is just simply how I mapped the ordinary differential equation that we got from Kirchhoff's rules or understanding electrical circuits for an analog circuit, mapped it into the digital domain. And if I rearrange that equation in the digital domain, I rearranged it here, it tells me how to calculate the output at time I from the input at time I and the output at the previous time. So time I minus 1. So if you look at this equation here, it's got the output at sample I, the output at sample I minus 1, so the prior output sample, and the input at time I. And so I can just rearrange it for yi, and it's this equation here where, just for convenience, I introduced this new parameter, right? This new constant. It's always the same, no matter what sample. I just called it alpha. And alpha, if you go through the little bit of algebra here, is just the time between adjacent samples divided by the time between adjacent samples plus RC.
So we have that yi minus 1 previous sample. So that means the output of output, right? Previous output. So do we have like previous output?
Yeah, so you'll show, when I start the code, you'll see I might have to do something special for the very first sample, because for the first sample, right, you don't have the prior one. But suppose, so this is a problem. So this is a very important question, actually. It's a good question to ask, because it came up, I think, when we were dealing, say, with the heat equation or the wave equation, right? You had to calculate the amplitude of the wave or the temperature of the rod. You had to know the prior sample, the temperature of the prior sample, or the amplitude of the wave of the prior sample. And so you had to handle that in your initial condition. So when I write the code, we'll make an assumption about that very first step. But once you've got to, so we'll make an assumption about the output sample for the very first input sample. And actually, we're just making the same. But then when we go to the next step, right, the next time, then at that time, we've got available to us both the input at that time and the output at the prior time. So once we got past that first step, then we're set to go. We always know what our current input is and what our prior input was. So yeah, that's a very, very good point. When we talk about this type of sampling, look, I called this one, here's the input We called this one the inertia. Is so in this particular filter corresponding to an RC circuit, the output not only depends on the current input, but it has some inertia based on the prior output, which was obviously a function of all the prior inputs. So that's kind of the drag or the inertia that's happening. So this is this code here. I actually implemented the algorithm. It's a recursive algorithm because it depends on the input and the output for the low pass filter. And I made it a user function. And I also did one for the high pass filter because it's done in a very similar way. And again, it's a user function. Now, in both of these user functions, you'll see that I pass a few things. I pass the RC, the product of RC for the filter, because that sets really the definition of what we mean by low frequencies, high frequencies. It sets the cutoff frequency. So we need to pass the RC to determine the cutoff frequency. I need to pass the sampling rate, so the time interval between successive samples in my digital world here, my discrete times. And also to my functions, I'm just going to pass an array that corresponds to the input, the sequence of samples on the input, and it's just going to pass back to me an array that is the output, the sequence of samples on the output. So one call to this function, the low pass filter function, one call to the high pass filter function, I'm going to pass these few things and I'm just going to get back the output. Okay, so here in this second cell, this is my user function, that is the low pass filter. And here is my function that is a high pass filter. The former one, the low pass filter, I derived the difference equation. But you could follow the same procedure to derive the difference equation for the high pass filter. So in both cases, if you look at when I call the function arguments for the low pass filter or for the high pass filter, as I mentioned, I'm going to call it with an argument that is the RC time constant. It's going to set the scale of low and high frequencies. Actually, I noticed in this one, I called that RC, and here I called it tau. It's a time constant. I'm going to pass the frequency at which I sample the data. So the time between adjacent samples, that's the DT. And I'm passing the signal. So X is the signal. Okay, so let's imagine I call the low pass filter. And I enter into this little low pass filter code here. So firstly, I define an array for the outputs that is the same size as the input array. So I'm just making a Y filled with zeros corresponding to the number of elements that was in the input. I use that kind of convenient parameter, alpha, because that's kind of the coefficient with which I combine the current input and the prior output. So I define alpha in terms of the DTs and the RCs, or the DTs and the taus. For the very first sample, it's exactly the issue that you raised. What do you do to the first sample because you don't know the prior input? So all I'm doing here, actually, I forgot what I was doing here. I take this is a common way of handling it. This is my input at Y0 based on my this is my first output based on my first input. And you see here, there's just alpha times the input, as if, so if you went back to look at the full equation here, it's as if at the prior time it was 0. The output was 0. So that's the assumption that we're making. Then, after I've made that very calculation of the very first output sample, I calculate all the remaining output samples based on this little recursive relationship here. So it's this superposition of the current input, X, with the prior output, Y, where they're multiplied by this coefficient alpha, or 1 minus alpha, and that's what we had derived. And then finally, I return that array Y. And there's a similar procedure here. You can see it for the high-pass filter. So let's define those two user functions. And then I'm just going to run them, and I'm going to show you how the filters work on a step function, how the filters work on a sinusoidal signal, which is what we discussed when we tried to characterize filters. We said we could characterize them by their step function or by their frequency response. Okay, so this cell here, just one cell defining a few numbers. These are the few numbers associated with, firstly, the particular filter. So I want to define the RC time constant. So in this case, I defined it as 10 seconds. And then two other quantities describing my kind of discrete time. So the time intervals is dt. So it's 1 second between successive ticks or discrete times. And then I'm going to make an array that has 1,000 of those ticks, 1,000 of those samples. Okay, so now I'm going to imagine I'm going to put in a step function. I'm going to go from, see, in this case, I kind of went from 0 volts to 1 volt, say, and then after some time delay, 500 seconds, I'm going to go back to 0 volts. So I've got a simple step function across these 1,000 seconds, 1,000 discrete seconds. And then I'm going to put that step function into the filter and see what I get out of the filter. What's the output of the filter? So firstly, I'm going to make the input function. And so that's done here. So I'm going to make an array of times. In our case, there's going to be, 1,000 times. That's the maximum time for 1,000 seconds. That's with this linspace here. And then I'm going to make an array for the input. That's going to be xi. At first, fill it with zeros just to initialize it. But then to make a step function, I'm going to fill the first half of it with ones. And then the second half of it, I'll leave to be the zeros. So it's like I've got suddenly, I go to 0 volts. Sorry, I go to 1 volt. I stay at 1 volt for 500 seconds, and then I go back down to 0 volts for the next 500 seconds. And we're going to take that step up and then step down, and we're going to shove it into the low-pass filter. And so to put it in the low-pass filter, I just call the low-pass filter function, user function, with the input that I've just defined, and it's going to return to me the output. And we can plot that. So here I'm just plotting in a simple way in magenta the input and in green the output. So if we run this, so magenta was the input, and it's just this kind of square wave, this step function. And then in green here, this is the output of the filter. And so you see here, right, it's not an immediate response. It can't pass the high frequencies. So when you go from 0 to 1 volt, it takes some time determined by RC to climb up to 1 volt. The high frequencies are attenuated, only the low frequencies pass. And then likewise, when I go from 1 volt down to 0 volts, you can't immediately go down to 0 volts. High frequencies are attenuated. It takes some time determined by RC to return to 0 volts. And so this shape here in green, this response to the step function characterizes the filter, it actually describes completely the filter. If I was to change, let's make this longer, right? If I make RC longer, so that's a time, I'm making it longer. That means it'll make the cutoff frequency smaller. So frequencies that would have got through with RC of 10 will no longer get through. So it's rejecting more high frequencies, letting through less low frequencies. So then I see that it takes much longer, 10 times longer, to reach 1 volt. When we switch on the voltage on the input, it takes 10 times longer to reach 0 volts when I switch off the input, the 1 volt on the input signal. So this is the effect of the time constant. And again, this curve here completely characterizes this filter. If I was to change this to 1, and rerun the filter. Now I've increased, I've shortened the time constant, sorry, which means I've increased the cutoff frequency. So I'm going to let through many more high frequencies, and than I would with the much larger RC time constant. And so this allows me to respond much more rapidly to that change of the input, respond much more rapidly, change of the output. It's very hard to see. It's not immediate that we reach 1 volt. It's not immediate that we reach 0 volts. You see a little magenta down here, a little magenta over here, but it's a much, much faster response. And again, that curve in green represents the response of this filter. It completely describes this filter. So that's the step function response for different filters. And I hope you see how, a bit like the partial differential equations or the coupled differential equations, in those partial differential equations, coupled differential equations, there were some cases that you could analytically solve without too much work. You could find out, that a solution of Laplace's equation or Hütter equation, or a wave equation, or some simple initial or boundary condition. But in general, it would be impossible to solve analytically for some more general initial or boundary conditions. Exactly the same is true here, right? We could solve, the problem of the step function be applied to a low pass, high pass RC filter. We can solve that analytically, but just about any other signal that we would choose to apply to the inputs of these low pass, high pass filters, we wouldn't be able to solve that analytically. We can only solve it digitally with this digital filter. So when we studied the step response, we first made a step. So we first made the input. Then we applied it to the input of the filter, and we got the output. And we plotted them against each other. And we're going to do exactly the same thing here. I'm going to make the input, which is now going to be a sinusoidal signal. I'm then going to apply it to the filter. And I'm going to get what you get out of the filter. So this time, when I create my input signal, I'm going to create it to explore the space with several different frequencies. So omega is going to be the frequency of my signal, the angular frequency of my signal, the number of radians per second. My frequency has an amplitude, it has a phase too. I won't change those things. I'll just change the frequency. So I define omega, and then I want to create a time array as we did before. That's my consecutive time samples. And then I want to create my signal, xi, as I did before. I initialize a whole bunch of zeros. And then I'm going to fill it with a sine wave. So look here, in this loop of all the elements of that array xi, I assign each xi to be the value of this sine function. Here's the amplitude, here's the phase, and here's the frequency that I'll explore a little bit. And then once I built that input signal, I can just call my low-pass filter with it as an argument and get my output signal. And then I can plot one versus the other. So we'll try that out. Magenta is the input, and the green is the output. And you see, in this case, I picked a low frequency compared to the other frequencies I picked. So this is a low-pass filter. The low-pass filter will pass low frequencies. And so basically, I'm getting whatever I put in, at a low frequency, I'll get that signal out. I'll get it out maybe at a slightly reduced amplitude, and I'll get it out at a slightly reduced phase. And certainly for the phase, you see that here. There's a slight phase lag of the output. And maybe you see that the output signal is slightly smaller than the input, maybe not. Anyway, so that's the response for that particular frequency. So now let's turn the frequency up. So remember, this is a low-pass filter. It's going to let through these low frequencies. Now let's make the frequency 10 times larger. And this is what we see. So now you see, the signal does pass through, but that output in green has a smaller input amplitude than the input in magenta. So it's being attenuated a little bit, and it has clearly a significantly different phase here. So these are the effects of the filtering. We're still we've not got above the cutoff frequency, so it's not being attenuated too much. The phase is not changed too drastically, but it is attenuated and its phase is changed. If we go to 10 times higher frequency, now you see big effects of the filtering. So you see big effects of the filtering in that, remember again, magenta is the input and the green is the output. You see the very high frequency oscillations here in the input and the output. But you see from these sort of bands that now the output is maybe 5 times smaller than the input. So there's been a big attenuation for this high frequency. It's impossible to see here actually on this scale, but the phase is now very different for the input and the output. And so this is the effect of the filtering. And again, you could imagine the nice thing about this digital signal filtering, well, look, I just applied a step function, or I just applied sine waves, and I was able to calculate the outputs, but I could apply any signal I like, any shape of signal I like, and explore the filtering. And that's kind of what the real power of the numerical filtering, rather than sort of analytically calculating filtering.